Welcome to Chip Chat Conversations in the Cloud, a weekly podcast with IT leaders who are driving the future of a software-defined infrastructure-based data center.
Good morning, good afternoon, or good evening, wherever you may be listening to this Chip Chat Conversations in the Cloud. My name is Jake Smith, and I'm here with Matt Meinel, Senior Director of Financial Services at Levyx. Matt, welcome to the program.
Thanks very much, and glad to be here.
So, Matt, talk a little bit about your role at Levyx, and talk a little bit about Levyx, the company, and how you're transforming the financial services industry.
Sure. So my role at Levyx is really to connect our technology, which I'll go into in a second, with financial end users and fintech companies that can embed our technology. Our company's story is most of the founders came out of the solid-state storage industry. They worked for manufacturers of SSDs in the early days. And Levyx was born out of the frustration with the software stacks on top of SSDs. What they found is they were putting all this power and performance into the SSD devices themselves, and then you'd put them under a database, and you'd get like a 10% performance increase or 20%, which was okay, but nothing like what the actual hardware could do. So they identified the problem as the algorithms that were inside these databases and file systems. So what they set out to do is just build all new algorithms for the core engines for accessing data on solid-state drives using multi-cores. And so they came up with a super fast, lock-free data engine that performs at exceedingly low latencies. What we've been doing since about 2015 is embedding that in various customers' products. Then on top of that, we've taken that same engine and we've looked at the issue of accelerating compute platforms, both on the cloud and on-premise. So we've done a lot of work with Apache Spark, where fundamentally we're allowing Apache Spark to use SSDs and up-and-coming fabrics like Intel's 3D XPoint Optane drives in place of RAM. So we get a great scale-in phenomena, which allows you to run an Apache Spark program on a much smaller cluster than you'd otherwise need when you attach, say, Optane drives locally to those nodes. So that's what we're up to.
Can you talk a little bit about where Levyx software is able to improve not just the legacy architecture, but the actual financial model for backtesting capital markets?
We've been doing a project with Intel's PSG team where we've taken that analytic framework that I just mentioned that uses SSDs in an Apache Spark framework, and we've added to it the ability to use FPGA accelerated computations, such as would be done for risk analytics at a large investment bank. And what we found with that is that the FPGA can outperform GPUs on these calculations, but one of the constraints with the FPGA is you actually have to have a way of feeding input data into the FPGA fast enough and pulling the results out of the FPGA fast enough to actually achieve overall benefit. And that's what our architecture has been able to do by scaling in and being able to put a lot of the data on a single node on very fast SSD and using the low latency that comes from Levyx's stack basically bypasses the kernel. So you can imagine that applications that are trying to access input data that's persisted on disk are basically being able to get that data at speeds like tens of microseconds, right? And then we're doing some pipelining on top of that. So that's why we say we can come close to replacing RAM for these large data sets. So we bypass the kernel. We have a bunch of optimization. We have super fast indexing. You're just going through a single index to get to any item on the SSD. So in the FPGA case I just was telling you about, we're actually pulling data using 50 CPUs to pull data off of these SSDs, put it into the FPGA input buffers, and then using another 50 cores to pull it out. And with that kind of pipelining, we're able to keep the FPGA pretty busy. And of course, you can go to multiple FPGAs per server or even multiple calculation engines per FPGA card. So you get a huge bump in terms of the number of calculations you can do versus pure scale out on CPUs. which also means you get a real cost benefit.
Well, your end-to-end application costs go down, your cost per transactions go down, your ability to actually do more backtesting, to actually de-risk your application environments for your calculations. Talk a little bit about how you use not only Intel Optane, but FPGA accelerators for the Stack A3 backtesting use cases, and then talk a little bit about how you specifically use the FPGA accelerators.
First off, you mentioned Stack A3. That's an industry benchmark published by Stack Research, which is kind of a consortium of banks and vendors that come together to build standard benchmark workloads so that you can compare across multiple different kinds of technologies. And the specific test we're talking about is taking a trading model, like would be used in a high-frequency trading setting, and backtesting it to figure out what parameters would be optimal, would create the most trading P&L, given a set of historical tick data from the industry. So the idea is you run this data through the model with lots of different parameters being simulated, and the goal is, how many simulations per second can you get through this framework? How much technology do you have to do 1 million simulations an hour? So what we're doing specifically with the FPGA accelerators using industry standard libraries that Intel has put out called FinLib by Intel. It's an FPGA accelerated financial derivatives library. So it comes prepackaged with Black-Scholes and Cox-Rubinstein and other risk analytics well known to people in the industry. We were able to build our demo application using this in about 4 or 5 weeks, which is very fast. And in terms of the latencies, we are getting, just from a simple test with one FPGA and one engine on the FPGA on a regular old server, we're getting like 50 million options calculations a second, which compares to what you could do on a single CPU. It's almost 10x more. So talk a little bit about your software-defined data processors, Helium and Xenon. So Helium was our first product. It is a single-node key-value store. It's completely embeddable. It has all the features I was talking about before. It bypasses the kernel, can run directly with any block device. We've run it on very large RAM arrays down to very small processors like ARM processors, like would run in an iPhone. It's very fast. It gives you the ability to access billions and billions of individual values that you're storing in your database at very high speed and low latency. So that's Helium. And then on top of that, we've built Xenon, which is a clustered product. So what Xenon does is it adds a just-in-time compiler and a bunch of query analysis on top of Helium so that if you're running on a cluster and you have a bunch of data stored on your SSDs or Optane devices, when queries come in, basically we take that request, convert it, optimize it, do some just-in-time compiling, and then we run the resulting code on bare metal, basically directly against the drives. At the end of the day, that just results in better performance for the application.
One of the things that I'm always struck with is that these innovations that drive fundamental transitions in our economy have opportunities to be used for good and for bad. Do you think that having latency-free architectures with software-defined data processors like Helium and Xenon, do you think it adds volatility or decreases volatility in our markets?
Well, I actually think it's decreasing the volatility of the market. And let me use an example to explain why. In the stock market, for example, it used to be that people sat around and waited for companies to announce their earnings on a quarterly basis, and then the market scrambled around to adjust to that new information that came out as a point, 4 data points a year, right? Now what's happening is most of the advanced people in the market are doing things like, if I want to know what Walmart's doing, I've got satellite cameras pointed at Walmart parking lots, and I can predict via the traffic and the number of people that are populating all these different Walmart sites, I can predict on a daily basis how much their sales are, and I can incorporate that in the stock price. So there's less surprises. Same thing with crop yields and all kinds of other things that are information that markets are fundamentally trying to do. So I think in general, those are trends that are reducing volatility.
It's an absolutely great point. Is there anything else that you'd want our listeners to know about Levyx?
I'd love for you to follow us. Check out our website at levyx.com. Also check out the work we're doing at stackresearch.com. That's STAC research.com. We publish several public reports there that are available on both cloud platforms and non-cloud platforms. And hopefully by the time this podcast airs, there'll be some new reports on Optane out there as well.
Thanks, Matt. On behalf of Intel, my name is Jake Smith, and this has been Chip Chat Conversations in the Cloud with Matt Meinel, Senior Director of Financial Services at Levyx. It's been an absolute pleasure and an honor, Matt. On behalf of Intel and Levyx, we wish you a very good morning, good afternoon, or good evening, wherever you may be listening to this conversation in the cloud.